Okay, now we're going to get to the last problem set on this worksheet here on lecture number 9. Gas lecture number 9. So let's go ahead and take a look at what that's all about. There was your gas density. So let's start from this one right here. And let's say we have two gases. All right. We got hydrogen, which is diatomic, neon, which is monatomic. Hydrogen's going to be clipping a little faster if they're at the same conditions because it's smaller. And that's kind of what we're going to quantify here on this part of the lecture. Okay, so because these gas molecules move, they have kinetic energy. So we can say the kinetic energy of the hydrogen we'll call 1, and then we'll say Ke2 is the kinetic energy of the neon. Now, we know that on average, same conditions, those are the same. That's called temperature. So, therefore, you can set those two equal to each other because their kinetic energies are the same. The reason, again, hydrogen's moving faster, has the same energy as the larger neon molecule. So, remembering that kinetic energy equals 1/2 mv squared, we can substitute in on each side and say 1/2 m1v1 squared equals 1/2 m2v2 squared. And again, we're going to do a little bit of manipulation. This would be, again, a question where I said, how can you derive Graham's law for gas diffusion? So, what we're going to do here, this is just a little fancy moving the quantities around. The halves, of course, will cancel out. You just multiply both sides by 2, and those are goners. See the V12 you keep over here. Bring the V2 over. It's going to be on the bottom. M2 is on the top on the right, and then you slip the M1 over there. It's going to be on the bottom. So you will notice 1 over 2 equals 2 over 1. So it's going to be the inverse, but this is still mathematically, it's a little sloppy. So let's slide that up and take the square root of both sides. And then you'll get this squared over squared thing gone, which is kind of sloppy. And then also what we really want to know is the ratio of their velocities. Okay? And the ratio of the velocities can be determined then by taking the square root of the inverse of dividing the masses. So that's a fancy way of getting to what we call Graham's law. All right? We're actually not done with gas laws. We're going to do the most important one next week as it relates to our lab, but we are done with this particular worksheet. Don't show the whole derivation every time you do one of these problems. So we do problem number 23, and it says, what is the ratio of the speed of hydrogen molecules to the speed of neon atoms when both gases are at the same temperature and pressure? So one of the things you look at when you read problem number 23 is you're like, where are the numbers? How can I do a gas law problem with no numbers? And the answer is that you can, first of all, isolate which gas is which before we start plugging this into the formula. We'll call number 1 hydrogen because it said it wanted the ratio of the speed of hydrogen to the speed of neon. So it's very important that you set up the correct one as being number 1. Okay? So then you write Graham's law, because you see you're talking about ratios of velocities. And that's what Graham's law does for us. And now we can do the masses right here. We'll go back to just one place to the right. You don't have to dig up your stoichiometry periodic table. Just grab your regular one, go one place to the right. Keep it simple here. Neon 20.2 and hydrogen 1.0, but it's diatomic, so 2.0. So again, you're going to have to find the order of operation on your calculator. And this one, I'll let you figure out how to do this, but as long as you divide these out and take the square root of it, you should get 3.2. So the way you should express the answer is V1 colon V2, which is the velocity of hydrogen to the velocity of neon, equals 3.2. So be specific about this. Don't just say V1 over V2 equals 3.2. Make sure you're talking about what it is that you're doing. So all 3 of these steps I would like you to include, and certainly this one right here, because that tells you how you're dealing with the velocities. Okay, and since, by the way, there are no units of measure on 3.2. It's just a ratio. So it's a 3.2 ratio. So in other words, hydrogen is going faster, 3.2 times faster. Okay, that's the ratio between the two, and as it should be, because it's the smaller one. All right, I'm going to go ahead. We're going to do 24 together too, just as a little present to finish these up, because after we're done with this lecture, you should have done every one of these problems and gotten the answer for every one of these problems as we're doing it. Okay, so 24 is a little different angle. It says at a certain temperature, the velocity of chlorine molecules is 0.0410 meters per second. Okay, so that's about 4 centimeters per second. But that's their net velocity. You have to remember gas molecules. It hits this one, goes backs up, boom, 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 boom. It's just all kinds of collisions. So they actually move much faster than that if it were just straight line and never hit anything. But when you're measuring it, it's going to keep hitting things as it comes across the room. And you've all done that. You cook a pizza, and it takes a little while for that nice smell from the oven to hit you, and you're like, oh, I think it's done. But it doesn't just zip across the room, okay? You could also use smelt it, dealt it, fart mechanics, about how long that smell takes to get across the room. You've been studying that since middle school, I think. So, but anyway, one of the velocities. And then it says, what is the velocity of the sulfur dioxide molecules? Okay, so this one is going to twist things around a little bit. And it's very important that you get the numbering correct on this. So the way that this is problem set up, it's a lot easier mathematically to call this number 1, the sulfur dioxide, and you'll see when we get it set up why that's a little bit easier, because since it says what is the velocity of the sulfur dioxide, it's a little easier to solve for an unknown that is in the numerator. So just makes the calculations a little bit easier. But remember, they only gave you one number, which of course was the velocity of the chlorine as they bang and collide with other molecules and speed across the room, going at a rate of 0.0410. And of course, the M2 chlorine is 35.5. You double that up, you got 16 times 2 is 32, plus I believe this is 32.1, and just using your periodic tables, go one place to the right, divide those, take the square root, and then multiply it by the 0.410. And again, there's no right or wrong way to punch that into your calculator unless you get the wrong answer. So make sure that you're communicating correctly with your own calculator on this, and use something that you can use on the test, because you cannot use your phone on the test. So get used to using those scientific calculators. All right, and then we solve for V1, and of course all these guys have 3 sig figs. So turns out that the sulfur dioxide molecules are clipping along at 0.432 meters per second. And if you look at it, they're a little bit smaller. That's the mass of that one. So that should make sense. So you can always finish these problems by doing that. So you're welcome. You have now finished 23 and 24, and you've got good examples in your notes, and you'll be ready for this type of problem on the test. So awesome. Just make sure you now know how to do 1 through 24 on this worksheet, and then you will be in great shape moving forward. Take care.